Hello everyone, today I want to explain about metamers. Metamers, what is the definition? Compounds having the same nature of functional group but different nature of alkyl group along the polyvalent functional group. Polyvalent functional groups are which shows metamers or metamerism. Generally keep in mind this is a oxygen, this side, this side. If it is R, here R dash. Next, oxygen, and here oxygen, R dash. So different in this alkyl group, different in this alkyl group. If it is present, then this shows the metamers. If any one side, that alkyl group, if it is same, for example, these are same and these are different, but it do not show metamers. Compulsory both side different alkyl groups are required. Then only it shows the metamerism. One example I will tell you. Consider like this. Or one more consider this is. Here this side propyl is there and this side ethyl is there. So this one break and right here. Then what happened now? If you observe this ethyl is same is there. Then this side and this side different is there. But right side both are having same, therefore do not show metamerism. Now if you write like this, no. Now observe here propyl, here ethyl. And here ethyl, here isopropyl. Like this also don't consider. Anyway, these consider same side. Therefore, these two are do not show metamers. Compulsory both side different alkyl groups required. They are called metamers. So now I can write 1 minute. This is called metamers because here how many carbons are there? 3. Here also 3. But here 1. But total number of carbon how many are there? 3 plus 2 5. Therefore what you have to do, you change it and you write like this. Then now 1, 2, 3 and 4. And this is 5. Then these two groups are different. Therefore these two are metamers. Keep in mind metamers mean both sides of a polyvalent functional group, alkyl group should be different. Either side of the polyvalent functional group different required. That is called metamers. So now these are the polyvalent, left to right different alkyl groups required. These are different alkyl groups. This side different alkyl group. This is a polyvalent functional group. So these are different alkyl groups. If it is present, then it shows a metamers. Now, metamers. Polyvalent functional group which shows the metamerism are. This is secondary amine, tertiary amine, amides, and this also amide, but it is depends on the alkyl group. This tertiary amide and thioesters. These will show the metamers. I will give some functional group. For example, first ether consider, thioether consider, ketone consider, and ester consider, and amine consider, that is called secondary amines, tertiary amines, and acid anhydrides. Like this, any groups are there, these will show the metamers. For example, if you consider the aldehyde group, because this is compulsory hydrogen, that we do not show. Alkyl group do not show. Carboxylic acid do not show. Like this, any functional groups are there, do not show, because these are the fixed sides like this. Then when fixed is there, there is no change in the alkyl group. That's why they will not show metamerism. Next, some example taken here. C4H10O. If you consider degree of unsaturation for this 0, because the formula degree of unsaturation is half of 2C plus 2 plus N minus H plus X. This is a degree of unsaturation formula. Then now consider this is ethyl, this is ethyl. One of the carbon break down and this will attach here. Then you will get this is a propyl and this is called methyl. So now observe this side different, this side also different. So like this is there means that is called metamers. Observe these two are different, these two are different. Now taking the one more example. Consider this is C4H11N, N-ethyl ethanamine. So this is present on nitrogen, that's why N-ethyl ethanamine. Then one carbon breakdown and attach here, then it is converted into propyl group. Then it is called N-methyl propanamine. N-methyl propanamine. So alkyl groups are different. Alkyl groups are different. Therefore, this is shows metamerism. Now, one more example for metamerism, C5H10O. So, if you observe here, for this degree of unsaturation is 1, it means one pi bond or one ring will be present. So, now it is called pentane 3 one, pentane 2 one. So, here what are the ethyl is there. One carbon breakdown attached here, then it convert into which one? Propyl. These two are different, these two are different, therefore it shows the metamerism. Now coming to the tautomerism. Tautomerism is one of the most important topics. So now the phenomenon by which a single compound exists in two or more readily interconvertible structure that differ in the relative position of at least one atomic nucleus, generally hydrogen. Consider isomer exhibiting tautomerism are called tautomers. Tautomerism. Tautomer exists in dynamic equilibrium with each other. Now, these two consider double bond present in between the Y and Z. Next time, double bond present in the X and Y. So now, hydrogen bonded to X, here hydrogen bonded to Z. So this tautomerism two type. One is a dyad system, another is a triad system. That hydrogen movement between the two atoms that is called dyad. Hydrogen movement is between the three atoms that is called triad. Examples for dyad system, dyad tautomerism. Movement of hydrogen atom between 1 2 position. This is a 1, this is a 2. If this hydrogen shifted to here, then it is bonded to which one? Nitrogen. So these two are which one? Tautomers. Which one? Dyad tautomers. But if you take this cyanide, isocyanide, hydrogen cyanide, hydrogen isocyanide are tautomers. But if you take alkyl cyanide and alkyl isocyanide, these are functional group isomers, not tautomers, because here hydrogen is not moving, alkyl group is moving in functional group change. Therefore, they are called functional group isomer, not tautomers. Triad system. Movement of hydrogen between 1 3 position. So these are not IUPAC numbering, just movement where it is happening. Oxygen 1, 2, 3. So this hydrogen 1 is move here and this pi bond move here. Then it form double bond and here OH. This is called ene plus ol. So double bond mean ene plus ol. This will give enol. Keto form and enol form. In that this is a major and this is a minor, because carbon double bond carbon, this one, and carbon double bond oxygen. So this bond is stronger, this bond is weaker. Therefore, keto form is stable than the enol form. That's why it is very minor form. Now, condition for tautomerism usually present in the following functional group. So, like this group required, this is called carbonyl aldehyde ketone, imine, nitroso, nitro group. Like these groups are required to show the tautomerism. Next, condition for tautomerism. Presence of at least one hydrogen on the sp3 hybridized alpha carbon. So generally this is not always alpha carbon. Sometimes it may be called gamma carbon also. That is called 1,3 position, 1,5 position, 1,7 position, 1,9 position, so on, like this group position required. Now consider this is a 1, this is a 2, this is a 3, sp3 carbon. Compulsory hydrogen should be bonded to sp3 carbon, not to the sp2 or sp carbon. So that is one of the important thing. So this hydrogen comes to here, this will come here, then a double bond, and this is a OH. This is called enol, this aldehyde, but it is called simply keto form. So here it is a major and this is called minor. Condition for tautomerism. Tautomerism is possible if an alpha beta unsaturated carbonyl compound containing a hydrogen at its sp3 hybrid carbon, that is called gamma carbon. That is called fifth position, I think. So this is a 1, this is 2, this is 3, this is 4, this is a 5. Here how many hydrogens are there? 2. This will comes to here, this will comes to here, this will comes to here. Then you will get enol form. Then here this is a keto, this is called enol. So it has an extended conjugation. Which one is a extended conjugation? Like this double bond, like this resonance, it can undergo. That's why it is called extended conjugation. So somewhat this is stable. Coming to like this, it is open chain now. Then here also is 1, this 2, 3, 4, 5. Then this fifth one is a gamma carbon, sp3 carbon. One hydrogen comes to here, this will comes to here, this will comes to here. Then it form the enol form. Then keto-enol tautomerism, next example. A form of tautomerism between a carbonyl compound containing alpha hydrogen and its enol form. So this is a keto form, this is a enol form. This is only keto and this en plus ol is called enol form. Now keto form of monocarbonyl compound is more stable than the enol form. So it is greater than 99%. It is very less than 1%. This is because already I told this carbon-carbon double bond weaker, carbon-oxygen bond is greater. So it total overall it is explained like this. Here bond break, here bond, here bond break. So here carbon hydrogen bond breaker and this carbon oxygen bond break. So overall this energy carbon oxygen bond, carbon hydrogen bond. Here oxygen hydrogen bond and carbon carbon pi bond, oxygen hydrogen and carbon carbon. So this is weaker, this is stronger, therefore this is stable than this. Keto-enol tautomerism, reason why this table here mentioned CH, CC, C double bond or nearly 1500, here 1452 is there. So enol form less energy, that's easily break down, then it convert into back to keto form. So keto form is thermodynamically more stable by 48 kilojoule per mole. So this difference may be 48 kilojoule per mole, that's why it is more stable than the enol form. Example. So this is a keto form, this is a enol form. Here one alpha hydrogen. So this one comes to here, this one, then here enol form. Maybe right side also if you break that, then it convert like this. So any one side can break, that's why it is 98%. It is less than 2%. And coming to the aldehyde. So this aldehyde is 100% and enol form is a 0% or very 0.001% also, very less. Keto form of acyclic 1,2 dicarbonyl compound is more stable than the enol form. So why these are stable? Means this alpha, this is alpha, this 1, 2, 3. Therefore, one of the hydrogen from here comes here, then then enol form. In between this hydrogen bond form, I will show here CH3, C double bond O, C O H, and this is double bond CH2. So due to hydrogen bond is a stabilizing factor. Stabilizing factor. Next. However, in certain cases, the percentage of enol content predominates the percentage of keto content. When the stability of enol content predominant, minus I effect, resonance effect or hyperconjugation, intramolecular hydrogen bond. Already I explained the intramolecular hydrogen bond increase the enol content because it stabilize. Resonance also stabilize. That is called extended conjugation or hyperconjugation, and this minus I effect. So these are stabilizing factors. Next. Now already we studied this one. This 1, 2, 3, 4, 5. sp3 carbon comes to here. This will comes to here. This will comes to here. Enol. So now what happened? Enol content is major. Sometimes polarity of solvent also will affect the enol content. Measure of keto content is measure. So more polar. So polarity of solvent increases. Polarity increases. Enol percentage what happened? Decreases. Next. Keto-enol tautomerism, molecules having two carbonyl groups separated by one carbon. That is called 1,3-diketone. This is 1, this is 2, this is 3. That's what is called 1,3-diketone. This keto form again having the same hydrogen bond. I will explain here. CH3, COH, double bond, CH, C double bond O, CH3. In between this is what is a hydrogen bond, because here one hydrogen comes to here and this will comes to here, therefore enol form, and this enol form is stabilized. That's why it is nearly 76% and this is nearly 24%. This is a measure. Then same that hydrogen bond shown, that's why it is forward more than the backward less. Resonance stabilize here also, and hydrogen bond stabilize. See, due to this we have like this resonance. So resonance also stabilize. Then keto-enol tautomer, enol form of cyclic 1,2-dicarbonyl compound is more stable than its keto form. Again same factor here also. What is there? Hydrogen is there, and here also hydrogen is there. These are can shift like this or it can shift like this and can form hydrogen bond. So I will show here this is double bond, and here OH, and here double bond. In between this is what is a hydrogen bond. So hydrogen bond is a stabilizing factor. And one more thing here, these are the lone pairs, and here lone pairs. In between this repulsion takes, this is less stable, but here hydrogen bond stabilizing factor. Next, here 1, 2, 3, 4, 5. Here gamma position. This is having hydrogen. This will comes to here. This will comes to here. This will comes to here. So it is aromatic. Phenol. This is so phenol aromatic. So aromatic means more stable. Therefore, enol content 100% more stable due to aromaticity. Now, percentage of enol increases with the increasing stability of alkene. That is called hyperconjugation. So now this is alkene, no substituent. This is alkene, one substituent. Alkene, two substituent. Therefore, more substituted alkene is more stable because of hyperconjugation. So keep in mind here one alpha hydrogen. Here one of three are there. One hydrogen comes here, then it enol form. Alpha hydrogens are there. That's why this can form enol. But this is a major. This is which one? Minor, because substitution increases, stability increases. Then overall the conclusion is aromatic enol content is more, because general order of enol percentage, aromatic enol means like this phenol is more percentage, then beta dicarbonyl, then alpha dicarbonyl, then monocarbonyl. So beta dicarbonyl means like this. This is beta dicarbonyl. This is alpha dicarbonyl, and this is monocarbonyl. Okay. In case now overall, all isomers completed in the structural isomers. What are we completed? Chain isomer, positional isomer, functional group isomer, metamers, ring chain isomer, and tautomers. Among all, which one we have to give the first priority? Mean ring chain isomer we have to give first priority, then tautomers, then functional group isomer, then metamers, then chain isomer, then positional isomer. Okay. So this is about the today we discuss about metamerism and tautomerism.